So like he said, my name is Justin Hiemstra. I'm a student worker in CHTC's GPU lab. And today I'm going to be talking about testing GPU and machine learning framework compatibility. So I'm hoping this talk is fairly straightforward and easily digestible for anyone else who, like me, is currently gastronomically engaged. But lunch jokes aside, I want to try to frame this problem by first talking about what goes into running a machine learning job on CHTC using resources like GPUs. So anytime a researcher has a machine learning job that they want to run on CHTC with a GPU, they need three things. First, they need to write their machine learning code, and we're assuming that they're doing that in something like PyTorch or TensorFlow. And importantly, associated with PyTorch and TensorFlow, there's going to be some kind of a version number. So you might pick TensorFlow 2.6 or PyTorch 1.10. And that's a decision that a researcher needs to make when they're writing their code. Second, the researcher needs to pick a GPU. So researchers should have some kind of idea of what type of computational requirements their machine learning code are going to need. So if they can get by on an older K40, they should look at using one of those. But if they really do need a server with 4 new A100s, they can do that too. And the way we define what kind of GPU we want to use in HT Condor is by specifying a CUDA compute capability in the HT Condor submit file. So that's the second choice a researcher has to make. And then finally, the researcher has to pick a CUDA runtime library. And this is the bridge that handles the communication between the application space and the GPU. And it's what allows all of your machine learning code to go from the CPU to the GPU and for your machine learning code to actually run its computations. So these are the three choices that a researcher has to make when they're trying to run machine learning code using a GPU in CHTC. So this doesn't sound like a very difficult problem. It doesn't sound like it should be too hard to pick 3 versions and send your code off with HT Condor and have things work. But it turns out it's a little more complicated than we might think. So the first issue that we run into is there's overall a lack of documentation. Companies like NVIDIA, PyTorch, TensorFlow, they're all separate companies. And while they rely on each other for machine learning computation, they don't necessarily coordinate. And as a result of that, there's no central resource we can go to look at and see if I want to run PyTorch 1.10 with CUDA runtime 11.1 on compute capability 8.0. There's nowhere we can look at to see that those 3 versions are compatible. The second issue that we run into is as these frameworks and as the hardware matures, we've noticed that they've started to drop support for older frameworks and compute capabilities. So for example, after CUDA runtime version 9.0, NVIDIA dropped support for its Fermi architecture, which corresponds to compute capability 2.x, somewhere in that range. And then the third thing that we run into is anytime you have computing resources that are made up of discrete servers in a computing pool, you run into the issue of non-heterogeneous server configuration. So this screenshot here shows 3 different servers on CHTC that have all set different max CUDA runtime versions. And that's just one more piece of the puzzle that kind of adds to the headache and confusion of trying to pick compatible versions. So let's say we have a single tuple of versions. We have a CUDA runtime version, a framework version, and a compute capability. And we want to know whether or not those versions are compatible with one another. So to test that on CHTC, we kind of first make the assumption that researchers, admittedly, we're all kind of lazy and we're going to use nice, easy tools for installing our software. So we're making the assumption that this is all happening using Conda environments. And it's in the Conda environment file where we select the framework version and the CUDA toolkit version. The second thing we need for this code to run is the HT Condor submit file. And it's here that we define the compute capability and a timeout. And I'll talk about the timeout in just one second. But with these 2 things and any other code we need, or any other files we need for our code to run, we're able to submit the job. And this is kind of where the timeout comes in. You could imagine a situation where maybe we've requested resources that don't exist on CHTC. And if our code is unable to match on a server with the resources we've requested, we'd like that code to eventually time out so that it's not just sitting in idle indefinitely. And then finally, if our code runs or if it doesn't, we're able to do some kind of analysis to see whether it ran or whether it didn't. So the 3 things we look at are, did the job match? Was it able to find the resources we requested? Did the Conda environment resolve? That is, was it able to match all of the versions without finding any conflicting dependencies or anything like that? And then finally, the framework has to actually be able to communicate with the GPU. So if these three things happened, our job should run and it should succeed. And if any of those fail, our job will kick back with some kind of an error file. So that's how we test a single tuple of versions. We're now interested in looking at all of the different versions we might be interested in combining to see which ranges of CUDA capabilities and compute capabilities and CUDA runtime libraries might work with each other. So there are three main issues when we start looking at this. The first is if we're testing frameworks like PyTorch, TensorFlow with different CUDA compute capabilities and different CUDA runtime libraries, the version space of things we have to test starts to grow combinatorically. And on an active system where research is being done, that'll start gobbling up resources and taking it away from the researchers who need those resources, which we don't really want to do with testing suites like this. So we need some way to kind of scale that search space back. The second thing is we need some way of automatically collecting the different test parameters we're interested in. So we don't want someone in CHTC to have to update CSV files as new compute capabilities are released or new PyTorch versions come out or anything like that. So we'd like some way to kind of automatically aggregate which versions are valid to test. And then finally, we're still going to be firing off hundreds of jobs. So we need some way of managing all those jobs in addition to the pre and the post processing that goes into that. So as I said, the first issue we need to overcome is kind of pruning back the version space so we're not testing tens of thousands of different versions. And the first thing to note is that on a system like CHTC, only certain compute capabilities are going to be available. It doesn't make sense to be requesting resources on Fermi architecture or compute capability 2.x if we know that CHTC doesn't have any 2.x compute capabilities in its system. So we query the system and we ask HTCondor to tell us which different CUDA capabilities do you actually have that you can provide me with, and we limit our search to only those. Second, we're assuming again that researchers are using tools like Conda to install all their software. So we really only need to look at the versions of these things that are available through Conda. For example, I think TensorFlow 2.4 is available and TensorFlow 2.6 is available, but they skipped 2.5 for some reason. So we don't test things like 2.5 if we know that we can install them easily. And then finally, we're assuming that the research going on is active, it's developing new things. So we don't really want to consider people running on legacy software. So we can ignore things like TensorFlow 1.x or older versions of PyTorch and really only consider the newest, latest versions. So we've now pruned the version space and we need to dynamically generate the files associated with testing each of these version combinations. So anytime we want to test one of these versions, we need a few files for that test to run. First, Conda is being installed on the execute node for each job. So each job needs access to a portable Conda installer. Second, each job needs its own Conda environment file, and this is where we're pinning the framework version and the CUDA runtime version. Third, we have the HTCondor submit file, which is where we've specified a compute capability that corresponds to the GPUs we want to use. And then we're also defining the timeout in the submit file. And then finally, we have some kind of a script that just sets up our Conda environment on the execute node and gets everything to run. So to dynamically generate these files, we're using just Python string formatting to pass versions that we're interested in into some kind of a text file. And then that gets written out on the submit node for HTCondor to use. So we have all the files we need. We've pruned back the version space. Now we need some way of running all the pre-processing to run all the tests that we're interested in and then to do post-processing. So it might be tempting to just set up a Python script that submits all the jobs or does all the pre-processing, submits all the jobs, waits for that global timeout that I mentioned, and then does the post-processing. But we've decided on a timeout period of around 24 hours. So to do that, we would have to leave a script running on the submit node, which is kind of in violation of the philosophy of what submit nodes are meant to do. So we'd like to find some way to do all this job management without leaving something running on the submit node. So how do we do that? We've all seen at this point, I think there was a presentation yesterday and we saw it earlier today, the directed acyclic graph workflows, and HTCondor supports a tool called Dagman. So in the context of this tool, we're using Dagman to first spawn a parent process that lives on the execute node. That parent process will then do all the version space pruning and the file generation. It'll submit all of the jobs that we're interested in testing. It'll wait 24 hours for that global timeout. And then after the 24 hours, it'll run a postscript to interpret the output of those jobs. So it's not being used maybe as complicated as it might be, but the thing to note is it's running that parent process on the execute node and not on the submit node. So we've run our jobs, that period of timeout has passed, and now we need to process all the output files. So for a job to have succeeded, 3 things have to have happened. First, the job has to find the resources we've requested. The environment has to resolve, meaning that, again, it didn't find any conflicting dependencies or anything, and it was able to install all the software we need. And then finally, the machine learning framework has to be able to see the GPU and run some kind of a basic operation that indicates that it's using the GPU the way we expect it to. So to do this, for each job, we scan the output and the error files, and we look for any keywords that might indicate the status of each of these conditions. So anytime a job fails, it'll say whether or not it might have been a conda resolution issue or whether or not the job didn't match or something like that. And we record those to see, just to understand a little bit better about what's happening in the system. So I think people should be able to see this okay, but this is a sample output of what's being produced by the tool. You can see here, let's see if I can, yeah, we have TensorFlow, and it was confirmed to work with TensorFlow version 2.6 on compute capability 7.5. And then we see that there's a range of CUDA runtime versions that have been shown to work with this version of TensorFlow and this compute capability. On the right, we have some invalid combinations that didn't work, such as TensorFlow version 2.4 trying to run on compute capability 8.0 with CUDA runtime version 11.4. And we can see that the reason that this failed is there was an environment resolution failure. So for some reason, Conda couldn't resolve this environment and it passed. And then we can see here are some examples of jobs that just weren't able to find the resources that were requested. So we have this tool and we need some way of routinely testing it without competing with researchers who are trying to use these resources also. And then we want to use the results of it to gain further insight about how the system is working. So what we're doing with it is running it quarterly, viewing the tables, and looking at anything that jumps out that might change or anything that's unexpected. This should give us some tools to debug the system if something suddenly crashed. Or if a researcher can't get their machine learning code to run, we might look at the particular versions they're attempting to run. And if it's in that table of invalid combinations, well, we can look and say, hey, that's at least the start of your problem. And then finally, this is kind of an open question that we don't have the answer to, but it might be interesting to look to see how the choice of versions you choose affects the runtime of your machine learning model, or whether or not it affects the outcome and performance of that model. So that's kind of a question that we still have that we're looking into. So that's a rough overview of the tool we've developed. The implementation of everything I've discussed today is up on the CHTC GitHub repo. So you're welcome to take a look at that, and I'll open it up for any questions.